So we have, we just finished chapters 5 and 6, I believe. And today's the day for that exam. No, 6 and 7, excuse me. 1, 2, 3, 4, 5, 8, 6, and 7. Now we're into chapter 9. And let me share before I start talking about something that's not visible. Here we go. All right. Chemical quantities. So what do we mean by chemical quantities? Well, actually, the balanced chemical equation gives you enormous amounts of information about any chemical reaction. Well, any chemical reaction that it's designed to describe. And we're going to see how to make use of the balanced chemical equation in a process called stoichiometry. All right, what does the chemical equation tell us? It actually tells us not directly the relationship of masses of reactants to masses of products, even though those balance also in a reaction. When you have a certain mass of a reactant producing a certain mass of product, then you know that the mass before and the mass after are going to be equal. But the chemical equation is based upon the number of atoms and molecules that are involved in a reaction. So we have to do, if we want to talk about mass, we've got to do some conversions. And that's inevitable because we don't have any instrument that'll measure moles directly. It's all measured in mass, volume, even concentrations, but nothing measures moles directly. But the chemical reaction itself is based upon moles, on numbers of atoms and numbers of molecules in the reaction. And that's what the coefficients tell us. The coefficients tell you the ratio of reactants and products to one another. And that could mean the ratio of atoms, right, if it's an element, or ratio of compounds. So here's an example. We have this. First of all, what are we reacting? That's one thing that the equation tells you. What are the reactants? Well, in this case, we have ethanol, the drinking kind of alcohol. And it's going to be burned. We're combusting it with oxygen. And the products are going to be carbon dioxide and water. First of all, is this equation balanced? Well, we should be able to tell that. All we have to do is count up the atoms. Right, we have 2 carbons on this side. There are 2 carbons on this side. We have 6 hydrogens on this side, and 6 hydrogens here, 2 times 3. And oxygens. We have 1 oxygen plus 6 oxygens is 7. So we have 4 plus 3 is 7. So this equation is balanced. And as I mentioned earlier, we can discuss this in terms of 1 molecule of ethanol reacts with 3 molecules of gaseous oxygen, which we know to be diatomic, and produces 2 molecules of carbon dioxide and 3 molecules of water. Now, if you add up the coefficients, you have 3 moles here, or 3 molecules there, and 1 here, So that's 4, but you have 2 plus 3, 5 on the product side. So the coefficients don't have to add up to be equal. The only thing that's equal on both sides in general is mass. Mass of reactant equals mass of products, and we've known that since Antoine Lavoisier discovered that law and published it. But we know more than that now. We know, in fact, that the number of atoms of each element have to be equal on both sides. That's why the masses are equal. Other things that it can tell us, instead of molecules, those coefficients also relate to numbers of moles. Right? 1 mole of ethanol plus 3 moles of oxygen gas yield 2 moles of carbon dioxide and 3 moles of water. Now, the neat thing about addressing this equation as mole ratios is that it's easy to convert from moles to mass. All you need for the conversion factor in each case is the molar mass of each reactant or product. So that's how we get back and forth from one to the other between moles and or numbers of molecules and mass. All right. Let's look at an example. Suppose you're a mining company, and you also have a side gig for partially smelting the ore from which you derive copper in this case. It's a very simple reaction. It involves just heating the ore. And most copper ores contain a mixture of both of these compounds, right? Copper 1 oxide and copper 1 sulfide in the same ore. Or if you find different compositions from different ores, you can combine the ores in the proper proportion to give you the ratio that you want. And that's typically what they do. So once you've mined the ore and you've ground it down to a powder, then you can heat it. And you get this reaction. These two compounds react with one another, and they produce copper metal plus sulfur dioxide. So I can imagine living near one of these smelting operations and having to smell sulfur dioxide all the time. It's kind of like working or living near a paper mill. Paper mills produce similar gases with different reactions, of course. Theirs is derived from sulfuric acid. This is derived from the smelting of the ore, produces the gas sulfur dioxide. So my guess is now that the Environmental Protection Agency has clamped down on these industries and said you have to clean that stuff out of your smokestacks, which they do. And it's a marketable product, so one stream feeds another. But back to the topic here. So we've got these two compounds together, we heat them up, and they produce copper metal and sulfur dioxide. Now, is that unbalanced? Well, the slide says it's unbalanced, and we can prove it to ourselves. 1 copper on the product side and 4 coppers on the reactant side. We know it's unbalanced. So we have to balance it first, right? And if we go through those steps that I've described before, it will take 1 mole of copper 1 sulfide and 2 moles of copper 1 oxide to produce 6 moles of copper and 1 mole of sulfur dioxide. So this also gives you, now that it's balanced, you know how much, or you can calculate, your engineers can calculate how much copper 2 oxide, copper 1 oxide, excuse me, that's required in proportion to the copper 1 sulfide to give you stoichiometrically equal amounts. That's what we say. It's the stoichiometric amount, the exact amount by mass of each one, and by moles, that gives you the reaction with as little unreacted reactants as possible. All right, so after balancing the reaction, we can say something about the reaction that's taking place in terms of atoms, molecules, and moles. All right, so 1 molecule of this sulfide and 2 molecules of this oxide combine to produce 6 molecules, 6 atoms of copper, and 1 molecule of sulfur dioxide. All right. So if we say, I should read the question, how many moles of copper could be produced? And if you start off with a dozen copper atoms, or if you want to end up with a dozen copper atoms, how many dozen, that is, how many dozen could be produced from a dozen sulfide and 2 dozen oxides? Well, as it turns out, you know, that might be, if we start off with a dozen, how many dozen copper atoms can be produced from a dozen molecules of sulfide? Right? So if we have a dozen molecules of sulfide, then we should have 6 dozen copper. As long as we have 2 dozen of these. So 1 to 2 to 6. So I'm thinking that that's the wrong answer. That should be 6 and 6. I think something's messed up with this slide. That should be 6 and 6. 6 dozens or 6 moles. If you have 1 of these and 2 of those, then you should have 6 of these. So that's wrong. That answer's wrong. That should be D. And I need to make a note of that and correct it. Okay. So that's what we can determine from a balanced chemical reaction. Here are other examples, right? Just this is the way the publishers of the book think will make sense. If we have 2 water molecules and we split them into elements, so this is the decomposition reaction. We decompose water into its elements. We get 2 hydrogen molecules and 1 oxygen molecule. Well, let's see, is that balanced? Well, let's see, there are 1, 2, 3, 4 hydrogens, 1, 2, 3, 4. Yep, that's good. 2 oxygens, that's balanced. The coefficients, of course, will be 2 water molecules yields 2 molecular hydrogen and 1 molecular oxygen. The same ratio is possible with 4, 4, and 2. Okay, so that's what it would look like if you use this ratio. But we know that the preferred coefficient ratios are the simplest whole numbers. If you need to make a bigger ratio, you just multiply by a factor once you've established your ratio. Okay? So the advantage to this mole ratio, let's use, let's see, I don't want to steal my own thunder. Yeah, I got an example coming up. the coefficients can be used to produce a conversion factor, right? Remember, all we need for a conversion factor is an equivalence. So with our previous, let's go back. With our previous reaction, hydrogens. What we're saying is this number is equal to that number, right? 2 waters equals 2 hydrogens. So if that's the case, then we can create a conversion factor by just setting one side equal to 1. Say divide both sides through by water. Like that. Then this becomes 1, and there's your conversion factor. It can be molecules, it can be moles, anything that counts things. So you can derive this mole ratio in the equation allows you to say, if I have 3 moles of water, how many moles of oxygen will that produce? Well, no, I've got my conversion factors set for hydrogen. So how many moles of hydrogen will that produce? Well, it's 6, right? 3 times 2 is 6, and the water's canceled. Divided by 2 equals 3 moles of hydrogen. Okay, that's a conversion factor. And you've got conversion factors here of any combination. You have 2 to 2, you have 2 to 1, you actually have 2 to 1 here. If you can measure how much of this you get from a reaction, you can infer that that's how much 2 to 1 is the ratio of how much oxygen you get. So we're finding out that balanced equations have lots of information that can be used to solve problems. And okay, I can see myself now, but if I open the slideshow, what it's going to do is oh, there we go. Okay, I'm seeing what I need to see now. I hope I've been sharing all this time. Have you been, Brett, have you been seeing the shared screen up to this point?
Yes.
Okay, good. Because if we can't see the shared screen in this format, then it's not being recorded the way I want it to. So that's good. That's good to know. All right, so now we'll continue. All right, the mole ratio, talk about that. Now we have an example here. With this example, we have, let's see if we can name this compound. Actually, it's got 3 elements, and I would say sodium silicon fluoride. That's probably not. Disodium monosilicon hexafluoride. I don't think that could be a polyatomic right there. It's not in our list, but that doesn't mean it couldn't be one. Silicon hexafluoride could be a polyatomic. I'll have to look that up. Anyway, is this reaction balanced? Let's ask ourselves that. Well, there are 2 sodiums here and 4 sodiums there. So that's 6 sodiums. That's good. 6 fluorides, 6 fluorides, and silicon, 1 silicon, 1 silicon. Okay, we're good. That equation is balanced. So how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with excess Na2SiF6? All right, here's the way I approach it. Once you get your equation balanced, let's see, 2. I'm going to leave the states out just for convenience. And then we've got 4 sodiums that yield silicon plus 6 sodium fluoride. Okay, once you have these equations, I like to follow a pattern. What I know about what's given, I write underneath. Okay, so we're given 3.5 moles of sodium. Yep, 3.5 moles. We're also told that this is excess. Right, so what do they mean by excess? They mean that this never runs out. This will, every atom here will be consumed in the reaction because there's plenty of this. That's what that means. So you can assume that all of that is used up and produces products. Then the question is, how many moles of sodium fluoride does it produce? Right? So that's the question. Moles. Now we have all the information that's given in the problem, and we can solve for that unknown. If we want to find out how much sodium fluoride we have, we got to start with 3.5 moles of sodium and find a conversion factor that will give us moles of sodium fluoride. Right? So now we know this goes in the numerator and this goes in the denominator. And for brevity and convenience, I'll leave out the moles part. What we're going to use here is the coefficient for sodium fluoride and the coefficient for sodium. Right? That cancels the sodiums. And then we divide that into 6 and multiply it by 3.5. Right? So instead of getting out my calculator, we'll just scroll down. Okay, there you go. There's your conversion factor that was derived from the balanced equation, from the coefficients. And now we know they're 5.25 moles of sodium fluoride produced from this reaction. Right? That is a form of stoichiometry. All right, here's another one. We have this equation, which may be balanced. Let's see if it is. C3H8 plus 5 oxygen yields 3 CO2 plus 4 water. Okay, let's see. 3 carbons, yep. 8 hydrogens, yep. 10 oxygens. We have 6 here and 4 there is 10. It's balanced. Now what else are we given? By the way, what is that? You don't have to know because that's an organic compound. That's propane. Right? So this is burning propane, just like you're cooking steak on your grill or heating your house or or water heater, whatever the case may be. If you use propane in your house at all, this is the reaction that you want. And it produces a lot of heat too. Okay, how many moles of CO2 are formed? Moles of CO2. When 3.74 moles of propane are burned. I should read the problem. I mean, it says what it is right there. 3.74 moles of propane are burned in excess oxygen. Okay, plenty of oxygen. And if you burn it outside, of course, that's obvious. There's plenty. Now, why are we making a point of this excess thing? Because before this lecture is finished, we're going to talk about limiting reactants. Okay, that's where we're headed with that discussion. But for now, all of this reacts and produces that. So how would we set it up? We say we have this one. And we want this one. So we need CO2 on the top and propane on the bottom. And 3 goes in front of the carbon dioxide, and 1 goes in front of the propane. Right? So the ratio is 3 to 1. 3 to 1. So that means we only have to multiply this times 3, which would be about 11 something. 11.2 is our choices. All right, so that gives us how many moles of each. Now, what can we do with that information? Well, at this point, all we've studied is the ability to convert moles into mass. So we could determine how much mass that was, right? 11.2 moles of CO2. Converted to mass, we just need to know what is its molar mass. Right? For carbon, that would be 12.01 plus 2 oxygens is 32. So let's see if I can do it in my head. 4402. Right? So I will need my calculator for this one because it's not on a slide. So if we have 11.2 moles of carbon dioxide, we have 400. Yeah, 493. You have 493 grams of CO2. Now, that's not really very useful unless you're a global warming hysteric. What we'd probably be more interested in, what's the volume of that CO2? But we haven't got to that point yet because that comes in the chapter on gases. So once we know that, once we know this number of moles, we have a way, once we study gases, to convert it to volume. So you know the volume of CO2. That's more useful for gases. Okay, so we can also say, well, how much propane did we use, right? That might be interesting to know. I mean, if you only have a 20 pound tank, one of those little short ones, then how much did you actually use? Well, let's see, we need a molar mass. Well, we need the starting point here, 3.74 moles of propane. So what's the molar mass of propane? Well, we need 3 times carbon, and we need 8 times hydrogen. 4411. All right. So that's 3.74 times that is 165 grams. Well, that doesn't help us much in this country because our tanks are filled by the pound. Right, so how many pounds does that represent? So we'd have to convert that to pounds. How many grams in a pound? Well, I happen to know that's 454. Okay. So 454 divided into that, we only used 1/3 of a pound. Right, so at that rate, that tank's going to last a long time. They've even got, I think they've got tanks that are made out of some polymers or fiberglass reinforced something or other. You can see through them. So all you have to do is sort of slosh your tank a little bit and you can see it move. Then you can tell how much liquid you got left in your tank without having to guess. All my tanks are metal, so when I'm in the middle of cooking a steak, they could run out. If I don't check them, you know, if I clamp them into my grill, then it's kind of hard to shake them and see how much is left. So it's always good to have a spare tank. Oops, well, we're probably going to erase that anyway. Let me see, before I finish erasing, let me see if there's anything else that's going to be said about that reaction. No. Okay, so I can finish erasing this. I got some ghosting down here in the bottom edge of my board. I tried sealing it with WD-40 and it cleans pretty good, but I missed a spot. Okay. In a stoichiometric problem, one where you're calculating masses of reactants and products in a chemical reaction, you need to follow some procedures. And by now, you've probably worked enough problems to know that first thing you have to do, especially if it's a word problem, is you have to write your compounds correctly. If you don't write your compounds correctly, then game over. You cannot go further. Once the compounds are written correctly and placed as reactants or products, then you have to balance the equation, right? And you've probably had a lot of practice doing that too. Then if you've got any masses of reactants or products for that matter, convert them to moles, because there's a great wall. Actually, there's several great walls in a reaction. Right? Oops. Those are barriers. You cannot cross those barriers unless you have numbers of something. In this case, we're talking about moles. You can't go from here to here or there to there. You can't go anywhere in that reaction equation unless you're converted to moles. So if we have mass given, then we got to convert to moles. Otherwise, we can't move. We can't answer a question. The question usually says, how much of something else? So convert masses of reactants or products to moles. Then you use the balanced equation and its coefficients to make the conversions that you need. If you're going from here to here, you want the conversion factor from there and there. Okay. And then if the question asks you, well, after you make the conversion, then if the question asks how much mass of the product is produced or how much reactant is required to make the product, doesn't matter. To answer the question, if it asks for mass, you got to convert back using the molar mass of the product or the reactant, as the case may be. Okay, so that's what stoichiometry is. Did we cover? Yeah, we have covered that. I'm sorry, we did cover it. Well, it was introduced. Let me put it that way. We didn't really cover it. But stoichiometry uses balanced chemical equation to determine amounts of reactant or product given information, other information in the reaction. So you can make those conversions. Okay. So in the real world, this stoichiometric ratio, if you have so much of this and so much of that, right, to produce products, then the stoichiometric ratio is the one where both reactants, in this case, are used up completely. They're all gone to produce products. That's a stoichiometric ratio. And if you have, say, 1 here and 3 there, then 3 moles of this will react with 1 mole of A. And whatever the mass that represents would be a stoichiometric ratio. But in the real world, experimental error alone will cause one of those reactants to be limiting. Right? Remember when at the very beginning of this course, I hammered the point. No matter what your measurement, there's always uncertainty, which means if you think you have 10 grams here, you may actually only have 9.98 grams. Right? So one of these is going to be limited. And in any kind of problem that you're given, if you're given exact amounts of each one, right? You're not given amounts of one and saying the other's excess. We're saying so many grams of this and so many grams of that one. Then you can bet with 99% assurance that one of them is limiting. One of them will run out first. And then the reaction stops. And you'll have some left over of the excess. All right? So here's an example. We're going to react chromium and oxygen. Actually, if you have stainless steel cookware at home, most of it's aluminum now because it's a lot cheaper than stainless. But if you had stainless steel cookware and you scratch the surface with your metal spatula, that reaction will occur in an instant. That's what stainless steel does. It has sufficient amount of chromium in it so that if the surface is damaged in any way, the chromium oxygen reaction occurs in a millisecond to seal that scratch. That's why stainless steel does not rust, because it has this protective coating of chromium oxide built up in an instant. Okay, so let's take this reaction, chromium and oxygen yields chromium 2, oxygen 3, right? Yeah. So what type of reaction is that? We talked about types of reactions yet? I can't remember. Well, we've got an element making a compound. That's a synthesis. It's also a combustion. Any reaction, I mean, it doesn't, you don't think of chromium burning, but it is a combustion reaction because oxygen is a reactant. And it's a redox reaction, oxidation reduction, because you have to transfer electrons from a metal to a non-metal in order to get that reaction. Okay, so let's get back to the problem. How many grams of chromium 3 oxide, is that the right name for it? Well, oxygen is 2 minus, so that's 6 minus. So that means 6 plus to balance that, split over 2, so each one is 3 plus. Yep, it's chromium 3 oxide. All right, so let's get back to, I keep digressing. 15 grams of solid chromium. 15 grams of solid chromium and excess oxygen. So if it occurs in the atmosphere, yeah, you got plenty of oxygen. So what's the question? How many grams of chromium 3 oxide can be produced from that? All right, so the question is, what's the mass of chromium 3 oxide that's produced from this reaction? Well, what we have to do is convert that to moles. Otherwise, we can't go anywhere with it. Well, before then, what else do we need to do? We need to balance the equation, don't we? All right, this one should be easy to balance because both of the reactants are elements, right? So we can say we need 2 chromium, right? 2 chromium. We need 3 oxygens. All right, how do you get 3 oxygens out of a diatomic molecule? Well, we use the fraction trick. 3 halves will give you 3 oxygens, right? So we need to get rid of the fraction. So we multiply the whole thing through by 2. That gets rid of that fraction. Right? So now this is going to be 4. This is going to be 3. There. And this is going to be 2. And we can check ourselves, right? 6 oxygen, 3 times 2. Yep, that's right. 4 chromium, 2 times 2. We're good. It's balanced. So that's probably what this slide is going to show. Balance the equation. Two, 3, 4. Yep. So we got balanced. Now we need to know how many moles of chromium are there, because we can't go anywhere until we know moles of chromium. So we need the molar mass of chromium. Grams. All right, so you look that up on the periodic table. Right? Chromium is a transition metal. It's right here. And it's 52.00, rounded off to 2 decimal places. All right, so 15 times 52 is 780. Moles. Okay, that's a lot. Now, we need to find out how many moles of chromium 3 oxide we have. We need a molar mass for chromium 3 oxide. So we've got 2 chromiums, so that's 52 times 2. And we have 3 oxygens, right? So 32 times 3. 16 times 3 is 48. Add those together and we get 152. 152 grams per mole. But we don't have moles of that yet. We've only got moles of chromium, right? So that has to be converted to chromium-3 oxide from chromium, right? So the coefficient for chromium is 4. The coefficient for chromium-3 oxide is 2. So that means we need half of that number. Right? 2/4 is 1/2. So we need 780 divided by 2 is 390. And that's so many moles of chromium-3 oxide. Oops. All right, so now we can convert back to grams. $152. Is that right? Let's see if I'm staying in pace with the, okay. I did it wrong, didn't I? And nobody said anything. .288. $144. Okay, now multiply that times 152. $21.9. There we go. Okay. Let's finish the slide. There we go. 21.9 grams of chromium-3 oxide from 15 grams of pure chromium metal. All right. I hope that's my only mistake for today. You can do it in one step as long as you know what conversion you're doing. You're converting, you can chain your conversion factors, right? Convert grams of chromium to moles of chromium, and then convert moles of chromium to moles of chromium-3 oxide, and then moles of chromium-3 oxide to grams of chromium-3 oxide in one step. If you're so inclined, because they're all conversion factors. That's it. I mean, you just chain them together in the right order. All right. Now, oh, we got another example. Tin 2 fluoride. where do we see 10,2 fluoride? Well, they say dental products, right? That's how they get fluorine into your toothpaste, as 10,2 fluoride. What we used to call stannous fluoride. And if you look on a tube of toothpaste, you may still see stannous fluoride as an ingredient. So it's made by this reaction. They use hydrofluoric acid on tin metal and produces 10,2 fluoride and hydrogen gas. Right? So what do you do with that hydrogen gas? My guess is they probably just burn it. It's just like oil wells. Remember, it used to be, not so much anymore, but it used to be, when an oil well was built, there was usually a mixture of hydrocarbons in that formation underground. And the gases come off pretty easy, right? Like methane would come off very easy because it's volatile and it's under pressure. So it comes shooting out the top. But if you don't want gas, if you're after the black gold, the crude, then you want to get rid of the gas. Because if you keep it around, it's going to explode when you don't want it to. So you have these flares running next to the hobby horse, you know, the pumping station going up and down, is getting rid of that gas before it has a chance to explode. So that's probably what they do with this hydrogen. They just flare it off. So is that balanced? 2 hydrogens, 2 hydrogens, 2 fluorines, 2 fluorines, and 1 tin. Yep, we're balanced. How many grams can be made from 55 grams of hydrogen fluoride? Well, if you have 55 grams of hydrogen fluoride in aqueous solution, that's hydrofluoric acid. 55 grams of HF. Right, so we know we can't figure out how much of this product can be produced until we convert to moles, because we can't cross any of those barriers without moles. So we need, what's the molar mass of hydrogen fluoride? Right. Hydrogen we know is 1.01. Fluorine, I have to look up. 19.00, rounded off. So that's 20.01. I put it in the right place this time. And we divide that into 55, which is 2.75. Okay, so 2.75 moles of HF converted to 10,2 fluoride. Okay, so we look at the balanced equation, and the ratio is 1 of these to every 2 of those. So for 2 of these, you get 1 of those. So we just take half of 2.75. 1.37. Okay, now we convert back to mass. So 10,2 fluoride would be 10. Let's see. Here it is right there. It's a, let's see, it's a metal. 118.71. And then 2 fluorines that we discovered were 19 each. So it's 38 total. So that's 156.71. Okay. And I get 215 grams of 10,2 fluoride. Okay, so it should be marked off as B. There we go. So these problems are fairly consistent, fairly straightforward at this point anyway. You probably guessed we're going to complicate things in a few minutes. All right. So let me keep track with my hard copies. Okay, we got those. We got that one. Now we're going to this one. All right, so now we're going to take a different approach, sort of. Instead of saying how much product is produced, we want to know. Hold on a second. Hello? Hello? This is he. Yes, Monday at 4. Thank you. Okay, bye-bye. Sorry about that. I always answer doctors. Okay, so the approach here is not how much product is produced, but how much water are we going to need as a reactant to completely consume 20 grams of phosphorus trichloride. Okay, right? That's good information. I mean, it's information that a chemical engineer would need when designing even a pilot plant. You know, how much of these resources are we going to need? Can we put the plant at this location and expect to get the feedstock we need to produce the product? If we can't, we better pick a different place. Okay, in this case, we want to know how much water. So rather than put it on the board, I'm just going to go with the slide here. 20 grams of phosphorus trichloride, we have to convert that to moles, right? This is a balanced equation, by the way. So we have to convert phosphorus trichloride to moles so that we can move over to how much water we need. So this is the moles of phosphorus trichloride. This is the ratio of the coefficients. 3 moles of water here and 1 mole of phosphorus trichloride here. So that cancels the PCl3 and leaves us with how much water we have, need of, how much water is required. 3 moles, which if we convert to mass, we need 18.0, I would just say 18.02 grams of water. And that says we need, for that much phosphorus trichloride, we need 7.87 grams of water. And for this type of reaction, you probably want pure water. As pure as you can get. You don't just take it out of the river or out of the municipal water supply. Otherwise, you're going to get side reactions, undesirables. You need pure water to do this reaction. And what do you get? Well, in this case, we get phosphorus acid, not phosphoric, phosphorus, because PO3 is phosphite. If it were phosphate, PO4, then it would be phosphoric acid. But it's not, it's phosphorus acid. And hydrochloric acid. Okay, now here's a little steeper mountain to climb. So I will do this one on the board. I'll be sure my my board's situated, right? Okay, so we have this balanced equation. It appears to be balanced. 6 x's, 3, no, that's not balanced. 3 x's here. Oh, yes, it is. Right, there's only 1 x in that molecule. What am I thinking of? 3 x's here and 3 there, there's 6. 4 borons, and 6 oxygens. 3 times 2 is 6. Okay, it is balanced. So we've got 6 x's plus 2 B2O3. That's otherwise known as diborane. No, wait a minute. B2O3. No, that's boron oxide. Boron is 3 plus. Right? It's fixed charge, so it's a type 1 compound, metal and non-metal. Excuse me. It's not a metal. Boron's not a metal. Look at the chart. Where does that black line usually go? It goes down here to the left of boron and underneath, and then over the top of aluminum and down. So boron is a non-metal. All right, so it's a type 3 compound. We say diboron trioxide. Okay, so that yields B4X3 and 3XO2. Okay, we're given that balanced equation, and X is unknown. We don't know what that element is, but we're given this information, and the question is, what is X? Right? What is that X? All right, what are we given? 175 grams of X. Right there. Reacts with diboron trioxide. If I just read my problem, I wouldn't paint myself into a corner. There it is right there, diboron trioxide, to produce 2.43 moles of this compound. 2.43 moles of that compound. What is X? All right. What do we need to know to identify X? If we have the atomic number, simple. Just look it up on the periodic table. But in lieu of that, if we can determine its molar mass, then we can get pretty close to what it is. Most of the molar masses in the table are sufficiently different from element to element that you can use molar mass to determine the element. All right, so what do we need for molar mass? I abbreviated MW for molecular weight. We need mass and moles, right? We got mass right here. We need to know how many moles is that, all right? So if we've got 2.43 moles here, how many moles of X do we have? The ratio is 1 of these and 6 of those, right? 1 and 6. So 6 times that equals what? 2.43 is 14.58. I'm going to hang on to the decimals just for rounding error. What did I say? 14.58. There we go. We got mass and moles now. So we just say molecular weight is equal to the mass per moles. All right. So we divide that into 175. And we get 12.00. Now we go to our periodic table and the increasing mass from top to bottom and left to right. So we just follow it along until we find something that's close. Looks like carbon. That's our unknown, carbon. Okay. All right, I mentioned earlier this stoichiometric mixture. Right? That just says that you have exactly the right amount of reactants so that they're all consumed. There are no reactants left. Okay, that's a hypothetical. That's pie in the sky. It never happens. But that's our starting place. Because a balanced equation is telling us the ratios of reactants that exactly balance one another. That's what the balanced equation says. So we can use that relationship to determine whether we do have a stoichiometric mixture or not. And those stoichiometric mixtures, if you have one, it's theoretical and it's given in a test question, something like that. In the real world, it never happens. All right, so we're going to use the Haber process. Remember, Fritz Haber and Carl Bosch modified it later. Actually modified it almost simultaneously. Once this reaction was known, then Bosch took it and made a commercial success out of it for his parent company, BASF. You realize that company was that old, BASF. I mean, this was back prior to World War I. BASF was in business. They hired Bosch to take Haber's process and make it economical. Okay, so we got this balanced equation, and this is what it would look like, right? If you could see individual atoms and molecules. These are nitrogens. So 1 nitrogen and 3 hydrogens, exact match, gives you, over here, 2 ammonias. And if you have the exact match for each one, you get nothing but product in the after the reaction. And that's stoichiometric mixture. However, what usually happens is one is excess and the other is limiting. So when we look at it this way, we've got these nitrogens that are unpaired. They don't have enough hydrogen to go around, right? So they're still left over after the reaction. These are used up. Those 3 are used up along with all of the hydrogen. So that means hydrogen is limiting. The reaction stops when the hydrogen runs out, and now you have some nitrogen left over. Okay, so that's the definition of a limiting reactant, the one that runs out first. And consequently, since it runs out first, it limits the extent of the reaction. Right? Hydrogen runs out first, leaving excess nitrogen. Once you have found the limiting reactant, everything else in the reaction, in the reactants, you could have another one, 2 more, 3 more, 4 more, whatever it takes. Once you find the limiting, the rest are excess. Okay, now, how do we determine which one is limiting? We go back to the definition, right? The one that runs out first will produce the least amount of product. So let's look at that as an example. If we got methane reacting with water to produce hydrogen and carbon monoxide, this is the balanced equation. Then if you have, these are methanes here, the black ones, and these are waters, the red and white ones. If the mixture is stoichiometric, then you get this many hydrogens and this many carbon monoxides. And the ratio of methane to water is 1 to 1. Okay? So the ratio here is given as 5 to 3. Okay, so we do have some leftover methane, right? One of these reacts, those two react, those two react, those two react. We have these left over right here. So we do have 2 left over. So these, now, what would be the consequences if we say, all right, let's say there's plenty of methane, water runs out. How much product will be produced, say hydrogen? Then you go back and say, all right, suppose we have methane of a certain amount and we have excess water. Then how much would it produce? How much hydrogen would it produce? And you compare those two values. The smallest one tells you the origin is limiting. Right? In this case, the water runs out first, it's limiting. So it only produces a certain amount of hydrogen, and that smaller number that we found by comparison is the reaction that actually occurs. I got a subscript there that needs to be fixed. Here. All right. So here are the steps. Right, we just talk them through and then we'll do a problem. Of course, you have to write the compounds and you have to write the balanced equation. That's prerequisite for anything you do in chemistry. Convert to moles so you can make the transition from one side to the other. Then you convert the number of moles of one reactant completely to the product. And you do the same thing for the other reactant. And then you compare them. And the smallest amount tells you the source was limiting. Now that you know that source is limiting, that's as much product as you can produce, then you convert that one back to mass. Okay, so here's an A and B problem. Could be anything. A could be any compound, excuse me. B could be any compound. We're told that the reactant A is 10 grams and the reactant B is 10 grams. What do you need? This first question. What information do you need to know in order to determine the mass of product that will be produced? All right. First thing you need is, what's the equation? A plus B yields what? Okay. Next is, once you know the product, the reactants and the products, balance the equation, because you can't go anywhere until you balance the equation. What else do you need to know? You need to know the molar mass of A and the molar mass of B. You got to convert each one to moles and then find out which one is limiting. Notice you're given a definite amount of each one, 10 grams of A and 10 grams of B. So you've got to be able to convert them to moles so that you can tell how much product would this produce how much product would that produce? And compare the outcomes to see which one is limiting. All right. Like I said, balance the equation. What are the molar masses of A and B and the product? All right. In this case, we're given, this is the equation, 1A and 3 B's yield 2 C's. That looks a lot like Haber there. Okay, so in this case, we have A plus 3B yields 2C. And we're given 10 grams of A and 10 grams of B. Okay. Now, how do we get from there to there? We need molar mass, right? So if we convert this 10 grams of A, we need to know the molar mass. So the molar mass of A is given as 10 grams per mole. So that means we have 1 mole of A. How about B? We have 10 grams of B. All right, it's given as 20 grams per mole. So now we have 1/2 mole of B. Okay, now we're also given 25 grams per mole is the molar mass of C. Now, to determine the limiting one, you don't have to convert to grams yet. All you need to do is compare the moles of the product by each conversion. Then, once you find the one you want, then you convert that one back to grams. So this would be converted by AC, and this would be converted by BC. So the ratios are 2 here and 1 there, and 2 here and 3 there. So 2 times that is 2 moles of C are produced. And in this one, you got 2/3 of that value, which is, let's see, 1 divided by 3. Oh, that's a third. 0.333 moles of C. All right, so which one's limiting? That one. B is limiting. That means A is excess. So now that we know the moles of C, we can convert it back to grams. $25 on the bottom. So 0.333. Let me see, did I do that right? Yeah, 2/3 of 0.5. That's right. I'm gun shy now. I don't want to make any more mistakes today. (1.33 times 10 to the minus 2). Grams of C. All right, there's 1 mole of A right here. 1/2 mole of B. Then convert, right? 1 mole of A. Oh, I made a mistake. Oh, it's a different question. Excuse me. All right, this is going to be difficult. I need to go back. So I got to unshare this. And then share again. Actually, I need to go and manually move it. Give me a second. Yeah, there. That's a good place to start, right there. Okay, share the screen. Start the slideshow again. There we go. Well, I thought I was right. What mass of product would be produced given that molar mass of A is 10 and B is C? No, that's right. Well, why are we doing this one? 3 moles of B required to react with a... Oh, we're using a different approach. Actually, this is not the best approach. All right, we get to the same conclusion, but we use a different method. If we convert A to B, we find out how much B is required to react with A. And we find that 3 moles of B is required, but how many moles of B do we actually have? We only have a half. So that means B is limiting. All right, I like the other way, where you say, what's the minimum amount? I mean, what's the total amount of product that can be produced? That determines which one is limiting, and now you've already got the moles of C that you can convert straight to grams. All right, so that slide needs some work too. I need to redo that whole slide, that whole set actually. So let me make myself a quick note. I want to change that. I just circle. I'll know when I take a look what it is. Okay. So now that you know that C is limiting, this is where they convert half a mole to 0.333 moles of C. Then we take C and convert it. Did I do it? I did it again. Did I? No, wait a minute. Yeah, I did it again. That's 2 mistakes today. This is moles. And then that gives us 8 grams of C. Okay. That's just a cautionary note. Okay, for this balanced equation, which is combustion of hydrogen, that's like the space shuttle engine. Most rocket engines now, they tend to prefer hydrogen and oxygen as their fuel oxidizer mixture, because it has a very high, what they call specific impulse, which means you get a lot of bang for your buck in a rocket. All right, now I'm going to have to position that again. Here we go. There we go. All right, so for this equation, the question says, which of the following reaction mixtures could produce the greatest amount of product? Okay, 2 moles of hydrogen and 2 moles of oxygen. What would that do? Okay, we're just investigating the mole ratios here. If you have 2 moles of hydrogen and 2 moles of oxygen, you only need 1 mole of oxygen, right? So it's excess. Limiting says 2 moles of hydrogen produces 2 moles of water, doesn't it? Right? Hydrogen's limiting. 2 moles of hydrogen and 3 moles of oxygen, same thing. You still only need 1 mole of oxygen, and it's just more excess than it was before. How about 2 moles of hydrogen and 1 mole of oxygen? That's a stoichiometric mixture. They're exactly balanced. And you still get 2 moles of water. 3 moles of hydrogen and 1 mole of oxygen. Now, oxygen is limiting because you've got 1 of these and you only need 2 hydrogens. So it's in excess. So oxygen is limiting and you get 2 moles of water, which means each one of these scenarios produces the same amount of product. Okay. All right, we got a different ABC, it looks like. We got an A plus 3B yields 4C. Okay. 3 moles of A react with 6 moles of B. Which of the following is true after the reaction is complete? Okay, let's look at that for a second. How many moles of B would be required for 3 moles of A? 3 times, right? 3 to 1. So you'd need 9 moles. So in this scenario, B is limiting and A is excess. Right? 3-1 says you need 9 and you only have 6. So this says B is limiting and A is excess. All right. So the reaction molar ratio is 1 mole of A per 3 moles of B. That's true. The mixture ratio, 3 moles of A and 6 moles of B. That's true also. Still the same ratio, 1 to 3, 3 to 6. Oh, no, excuse me. That's wrong. The reaction molar ratio is 1 to 3. Yeah, the reaction molar ratio is 1 to 3. The mixture ratio is 3 to 6, which is also true. Okay. Therefore, B is limiting, A is excess. Yes, that's also true. All right. So given these facts that we've established, which one of these statements is true? A is left over. If A is excess, it is left over. Test-taking technique. A is left over, A is left over, B is left over, B is left. If B is limiting, it can't be left over. So we can eliminate C and D right now. So we got to look at A and B a little closer. Why is A left over? Because you only need 2 moles of A and you have 3. That's true. 2 to 3 would be the correct ratio. 2 to 3, or 4 to 6. Right? The ratio is the same. 2 to 3. 1, actually, that's not right. It's not 2 moles of A, it's 1 mole of A. The ratio is 1 to 3. Or 2 to 6. That's what you actually are going to have. This is the stoichiometric ratio. And you've got 3 here. Right? So that's excess. All right, so A's wrong. A's left over because for every 1 mole of A, 4 moles of C. 2 moles of A and you have 3. Oh, that's true. Yeah. 2 is what you need, but you have 3. Yeah, A's true. All right. So let's say we have Haber again. Okay, and the question is how many grams of ammonia? How many grams of ammonia can be produced from a mixture of 3 grams each of nitrogen and hydrogen? So you have 3 grams here and 3 grams there. Okay? So whenever you're given exact amounts of reactants, you should suspect limiting. Right, so we need to convert this grams to moles. Right? So 3 grams of nitrogen is converted to moles by its molar mass, 14.01, I think. Yeah, 14.01. That's 0.2141 moles of nitrogen. Oops. What was my mistake? I was about to make another one. That's diatomic. Its molar mass is 28.02. So that means it's 1.1071. 1071. Three grams of N2 yields this many moles of N2. There we go. Okay, how about 3 grams of hydrogen? So that's 2.02. .485. Okay, how much ammonia can we get from that? So this one cancels H2, and this one cancels N2, and leaves us with ammonia. Right? So 2 ammonias for both of them, but only 1 nitrogen for this one, and 3 hydrogens for that one. So 2 times that, we're back to that original number. .2141. and 2/3 of 1.485. .99. Okay, now which one's limiting? This one. Nitrogen is limiting, and it gives us this many moles of ammonia. So now we can convert moles of ammonia to grams. So ammonia is going to be 14.01 and 3 hydrogens, 3.03. Oops. 1704. Times 0.241. 0.2141. .65. There we go. That's how much ammonia you can produce from that mixture using the Haber process. Okay. So now we're going to talk chemical engineering a little bit. Just scratch the surface, of course. There we go. All right. Percent yield. What do we mean by percent yield? Percent yield addresses the problem of reaction efficiency. There's no reaction. What we've done so far with these balanced equations is we're saying this balanced equation says 100% of a reactant yields a product. The fact of the matter is that never happens. There's always some loss in a reaction process in reality. So we quantify that by saying, based on mass, what do you expect the product mass to be? Then what do you actually measure when the process is complete? So that formula then has to do with theoretical yield, the maximum amount of a product that can be formed when the limiting reactant is completely consumed. And then the actual yield is the measurement of what is actually produced of that product. So if you have two products, you can't judge the efficiency based upon the mass of the wrong product. Okay. When you calculate the yield, it has to be a ratio of the same product. And most reactions produce one product of interest, and that's the one for the chemical engineer to focus. So it's a very simple formula. Actual yield divided by theoretical yield times 100 is percent yield. Right? And like all percents, we have to know the origin of the percent, because percent is a dimensionless number. It just means parts per 100. It doesn't tell you what the parts are. Are they mass? Are they moles? Are they volume? You don't know. So in this case, the formula is calculated using mass. Mass of the actual product divided by the theoretical mass that you would expect to obtain. All right. So for this previous problem, we determined that 8.33 grams of C should be produced with this mixture of A and B, and these other factors included. But suppose you actually do the experiment, you manufacture the product C, and you measure your outcome at 7.23 grams. What's the percent yield? A simple calculation. You just take 7.23 grams as the actual divided by the theoretical times 100. So we had 86.8% yield, which is actually pretty good. Now, where could a reaction go wrong in such a way as to produce less product than you expect? You could have losses from purification. Right? If you're going to produce C and one of them is excess, I forget which one, A or B, but if one of them is excess, that means it's still going to be there in the reaction mixture. But you don't want it. You want C only. You've already used up B, so you got to get the A out. Well, in the process, you might also lose some of your C in purification. Okay, that's one possibility. Suppose you have an incomplete reaction. You think all of B is being used up, but actually it's not. And then when you purify it, not only do you lose some of it from that process, you never had that to begin with because the process wasn't complete. And that's another possibility. A third possibility is maybe the reaction was complete, but it made the wrong product. We call those side reactions. Right? So it could happen to B, it could happen to A. If it happens to B, of course, you've got that loss. If B makes D, right, instead of C, then you've got less than you expect. Those are three that just off the top of my head I can think of. There may be others. Okay. So find the percent yield of a product if 1.5 grams of sulfur trioxide is produced from 1 gram of oxygen and excess sulfur via this reaction. Okay, let's do that. Two sulfurs plus 3 oxygens yields 2 sulfur trioxide. Okay, so we're starting off with 1.5 grams. Well, this is actual 1.5 grams of that product. So what do we need to know? If we know the actual, we need to find the theoretical, right? So with 1 gram of oxygen, right? And we're saying excess here. So we say 1 gram of oxygen makes, how much sulfur trioxide would 1 gram of oxygen make if all of it were converted with no losses? That's the theoretical. So 1 gram of oxygen, remember we have to convert to moles before we can find out how much sulfur trioxide there is. Right? So 1 gram of oxygen is 32 grams per mole. 32 divided into 1 is 3.125 times 10 to the minus 2. Moles of O2. Right? So we're going to convert that to SO3. So we have a ratio of 2 here and 3 there. So it's 2/3 of that number. Okay, so we'll take that number, divide by 3 and multiply by 2, 2.083. Times 10 to the minus 2 moles of SO3. Now, oops. We want to convert that to grams. Find out this is our theoretical yield. So how about sulfur? Let's see what sulfur is, and we'll add oxygen to it. Sulfur is 32.07. And then 3 oxygens is 48, right? 3 times 16. 80.07. Right. So 80.07 times that value, yep, that's right, is 1.668 grams. Theoretical. Now we do the calculation. What's the percent yield? Equals 1.50 divided by 1.668 times 100 equals 89.9%. They might round it off to 2. No, it should be 3. We started off with 3. I missed it by 0.1%. Actually, they missed it. It's probably a theoretical. The rounding error. Okay, so that's the percent yield for this problem. All right. So we got one more to go. Yep, one more problem to go. And this should give you all the information you need to work out the review document problems. Okay, we're given a balanced equation. We're reacting phosphorus with fluoride, fluorine, and getting phosphorus trifluoride. So that's our equation. Okay. Now, what are we given? Well, the question is, what mass of P4 is needed? What mass of P4 is needed to produce 85 grams of PF3? And this is 85 grams actual. We want to end up with that much guaranteed. If we know the reaction efficiency is 64.9% yield. That's 64.9% yield. Okay? So, how do we approach this problem? Well, the equation's already balanced. That's good. We know what we want to obtain. But the equation is based upon theoretical. Right? So what we need to do is come up with a value here, theoretical, that will take into account the percent yield. So the first thing we need to do is find out how much of this theoretical do we want. And we do that by 85 grams of PF3 and we have for every 100 grams of actual, we're only going to get 64.9 grams theoretical. Excuse me. This is actual. For every 100 grams theoretical, we only get 65 actual because this is actual. So that cancels and leaves us with theoretical. Now, I did it that way just to illustrate what that percent means. But for convenience, for quick calculations, all you need to do is divide that by 0.649. Right? And that's what this is. Divide 85 by 0.649. And you get 130.97. So you need 130.97 theoretical to find out how much of this you need. So we got to convert this to moles, right? So what's the molar mass? Grams of PF3. We need to convert it to moles. Okay. So I got to add 3 fluorines, which is 19 each, times 3, 57, plus phosphorus. So we look on a chart, phosphorus, let's see here, 30.97. 87.97. Yeah, that sounds reasonable. 87.97. All right, divide that into 130.9. 1.4888. That's moles of PF3. Now, how many moles of P4 do you have? What's the ratio? It's 4 to 1. So for these, for every one of those, so we take a fourth of that value, 0.3722. Moles of P4, because that cancels, that cancels. So now we need, what's P4? What's the molar mass of P4? 30.97 times 4. Right? 123.88. So we have 0.3722 moles times 123.88. 123.88 equals how many grams of P4 we need to start with to give us that much guaranteed product. $46.1. Now I can round it off. Of P4. Okay? So there it is in black and white and animation. The answer is 46.1. Okay, I think that's the last slide. Yep, that's the last slide. And we're finished early again. Normally we go till noon, don't we? Well, at least that's the nominal time frame. 11:50. All right. So I finished 48 minutes ahead. It would have been finished earlier if I hadn't made all those mistakes.